Last little section of chapter 3, organic compounds. So a lot of the terms and categories and things that we have in chemistry come about from historical reasons. So early chemists divided compounds into two types. They called them organic and inorganic, or not organic. Organic compounds were compounds that came from living organisms. Inorganic came from non-living things like rocks and dirt and air. So what they found was that the organic compounds were easier to decompose, to break down into their elements than the inorganic compounds. But they found that the inorganic compounds were easier to synthesize. A lot of the organic compounds, they couldn't figure out how to make them in the lab. And so this distinction between organic and inorganic makes sense in that context. Note that this is a very different use of the word organic than you see perhaps in the grocery store, where organic means it's not been sprayed with chemicals. In the chemical sense of the word, everything you eat, except for things like salt and minerals, is organic compounds. So today, we can make organic compounds in the lab. And the way we define organic compounds now is that they primarily consist of carbon and hydrogen. Now, other elements are going to be present, especially oxygen, nitrogen, phosphorus, and sulfur, but those are usually in the minority. Organic compounds have to have carbon in them. If it doesn't have carbon in it, it's definitely not an organic compound. This little section here is your very, very short introduction to the world of organic chemistry. There's a whole 2-semester sequence of classes in OChem. So we're just going to have this little baby taste of it. The reason that carbon is so special is that carbon bonds are almost exclusively covalent. You've asked me, well, what would the charge on a carbon ion be? And I've told you they don't really form ions, and they don't. But they do form covalent bonds. And when carbon bonds, it forms 4 covalent bonds. It can form single, double, and triple bonds. And it easily bonds with other carbon atoms or with other elements. And because of these characteristics, you can have long chains of carbon atoms. And so this makes very large molecules possible. And it can branch and form ring structures and do all kinds of crazy stuff that most of the other elements just don't do. Here are some examples of carbon bonding. These are all organic chemicals. Here's propane, where we see 3 carbons in a chain. And if you notice from this structural formula, all of the carbon atoms have 4 bonds coming off of them. Here's isobutane. Here we have a 3-carbon chain and then a little branch here. Cyclohexane, it's like the carbons are playing ring around the rosy. And they can do that. They can form these ring structures. But again, all the carbon atoms have 4 bonds. Here's ethene. This looks a little different, but this is a double bond. A double bond is 2 bonds. And so here the carbons still have 4 bonds. 2 in the double and then 2 singles. Here we have an example of carbon with a triple bond. And then here we have carbon bonding to oxygen as well. This contains mostly carbon and hydrogen. It's considered an organic compound, but it also has oxygen in it. This is acetic acid, which is what gives vinegar its distinctive smell. Any questions? You do not need to know. This is for illustration only. I'll tell you what you need to know. Any other questions? So we divide compounds into inorganic and organic, and then we divide the organic into hydrocarbons and functionalized hydrocarbons. You may think all these flowcharts are a little bit of a pain, but the universe is complicated, right? And when you start looking at the individual building blocks of the universe, there's immense diversity, and so we have to categorize them in order to make sense of them. So the hydrocarbons, as the name suggests, hydro for hydrogen and carbon for carbon, only contain hydrogen and carbon. Hydrocarbons are just carbon and hydrogen. And these are things that we use every day. They're present in oil, in gasoline, liquid propane, natural gas. All of those good things that help us lead our comfortable lives are hydrocarbons. We're going to get just a little taste of how to name organic compounds. So if we have a hydrocarbon with only single bonds, these are called alkanes. Why? Because they decided to call them that, right? It's like, why is my name Jody? Because that's the name my parents gave me. There's no deep meaning, sorry. If we have double bonds in that compound, we saw examples of carbon making double bonds, then those are called alkenes. So this is the alkane is the category name for hydrocarbons containing only single bonds. We change that ending a little bit, and this is the category name for hydrocarbons with double bonds. Alkynes, which if you pronounce it a little differently, sounds like all kinds. Alkynes have triple bonds. And then to name these, we have a base name and a suffix. The base name comes from the number of carbon atoms in the longest chain. And the suffix is determined by the multiple bonds. And so that's where we're going to reuse this ane, ene, and ein. So the base name depends on the number of hydrocarbons. So if we start at the end here, these prefixes are going to look familiar. Dec for 10, non for 9, oct for 8. But up at the beginning, these are weird. We used mono, di, tri, and tetra for our molecular compounds. For reasons that I do not know and don't want to go into, we don't use those for the first 4 in this series of organic compounds. It's meth, eth, prop, and bute. And those can be a little tricky to remember the order of. And so the mnemonic that I've always used is that Mom eats pickled bananas, which suggests that maybe Mom is going to be a mom again, because who would want pickled bananas but a pregnant woman? But that helps me to remember the order of those. And I still, when I look at those compounds, I still say, Mom eats pickles. When I see Mom eats pickles, I count with the words of that sentence. And then the suffix is determined by whether there's double or triple bonds or just single bonds. So for instance, if we have something that is CH3, CH2, CH3, I'm not going to draw the structural formula because it's tedious, but I'll tell you that only has single bonds. Then to name it, we look at the number of carbons. There's 3. And for 3, the base name is prop. For single bonds, the ending is ane, and so this is propane. If there was a double bond in there, it would be propene. If there was a triple bond, it would be propyne. Any questions? Here are some examples. So this is methane. We have 1 carbon. Meth is the prefix for 1 carbon. And we only have single bonds. You can't have double bonds if you only have 1 carbon. Here's propane. I showed you that one. Here is normal butane. We put the N prefix on there because this is a straight chain. And there are other possibilities. Because carbon can branch, there's lots of different possibilities. And so we're not going to get into branched compounds. We're going to keep it simple with just the straight chains. Here's pentane, 5 carbons, all single bonds. This one is called ethene because it's got a double bond with 2 carbons. And this is ethyne because of the triple bond. Any questions? The prefix, the first part of the name, is from the number of carbons, and the suffix, the "-ine", "-ane", or "-ine", has to do with what kind of bonds. Any other questions? Yes?
So the name is just how they're arranged
The name,
for the most part, other
the
than
name,
the prefix, which is how many carbons that are in it, right?
well, what the book refers to prop as the base name, right? This prefix N is telling us that it's all in a straight chain as opposed to being branched.
Okay, so like that, like these words consist of a prefix and a suffix put together with no middle, you know what I mean? So
That's one way to look at it, a prefix and a suffix with no middle.
right,
And so meth is the prefix and ane is the suffix. Meth means one carbon and ane means only single bonds.
right. So what if you have something in the middle, like methamphetamine?
Yes, what if you
I'm
had
just
something in the middle?
curious.
Methamphetamine. There is pages and pages and pages of rules on how to name organic compounds.
Well, because amphetamine is a compound by itself.
Amphetamine is a compound by itself, and meth is a prefix in the front that tells us about one of the functional groups that's attached to it.
Right? Okay, and then the ene is just shows that it's double bonded.
Well, actually in methamphetamine, it's AMINE, and that means it's a nitrogen compound.
Oh, I see.
Okay? Yeah. There's lots of questions you can ask, but most of them are going to go way beyond what we're talking about here.
So for this class, we're just doing the prefix and the suffix.
Yeah, we're just trying to keep it really simple.
Okay.
Yep. Then there are functionalized hydrocarbons. These are organic compounds that have something special in them. They may have one of those other elements, oxygen, sulfur, phosphorus, nitrogen, or even technically a double or triple bond can be considered a functional group. They're called functional groups because those special groups affect the function of the molecule. A hydrocarbon with a double bond will undergo some reactions that a hydrocarbon with only single bonds will not. And so the double bond adds function to the molecule. If we have a group of compounds with the same functional group, they're considered a family. So alkenes are a family of organic compounds, and alcohols are a family of organic compounds. So here are two examples of the alcohol family. The alcohol functional group is this OH group. This one is methanol because there's one carbon. It's one carbon, so we have that prefix meth, and now we've got "an" from methane, and we change the ending to "all" to indicate that it's an alcohol. This is isopropanol. Or also called 2-propanol. Propanol is the 3 carbons. So there's 3 carbons here. It's iso or 2-propanol because the OH group is on the second carbon. And I don't want you to get too worked up about that. The reason they're using isopropanol as an example is that is rubbing alcohol, isopropyl alcohol. And this is something that you may be familiar with. Can anybody think of another alcohol? Ethanol. Yesterday was the Super Bowl, and I'm sure the ethanol consumption in this country went way up. Ethanol, how many carbons do you think it has? 2. Eth is the prefix, if you will, that means 2. And so ethanol is 2 carbons and that OH group. As the molecules get larger, there's more possibilities and the names end up getting fancier. But again, we're going to try not to go there. But these compounds are going to have some similar characteristics because of the OH group. And that's why they're considered a family, the alcohol family. They also have some important distinctions. I recently read a very tragic story about 4 teenagers that were drinking methanol, which is racing fuel, mixed with Mountain Dew. They didn't realize that methanol was toxic, and 2 of them died. Methanol is not something that you can drink and be okay. Now, ethanol, which is the alcohol in alcoholic beverages, is also toxic at high levels, but it's, at reasonable levels, it's not going to harm you. Isopropanol, you shouldn't be drinking that one either, okay? So they have similar characteristics, and yet they're very different as well. Any questions? So here's an overview of the different families of organic compounds. So here's the alcohol family, here's the ending of the name, and this OH is the functional group. When we describe general formulas like this, R stands for a hydrocarbon, an alkane group, just carbons and hydrogens with single bonds. So this could be CH3, or it could be 5 carbons in a row, could be anything, but the OH is what makes it special. These are the ethers. Ethers have an oxygen between 2 other groups, etc. Now, do you need to memorize this table? No. It is in the text, and we're covering it. It might show up on a worksheet or something. There could be a question referring to this on the final exam. I'm not going to give you questions about functional groups on my midterm exam, but it could show up. So if you're one of those students that's trying to ace everything, then yeah, go ahead and learn those, because you're probably going to go on and take OChem, and you'll need to memorize those anyway. But here's that word, amine, and this is the functional group, NH2. So methamphetamine has this NH2 group in it. I can tell from the name. Any questions? So let's draw the structural formula for nonane. Well, how many carbons does nonane have? 9. You should be able to do the regular hydrocarbons. So we need 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's a typical kind of math that you find in OChem, is counting carbon atoms. Each of these carbon atoms has to have 4 bonds. So I'm going to draw the bonds in. And 4 is really nice because it's up, down, right, and left. Very easy to see. Nonane is a hydrocarbon with only single bonds. If it was nonene, it would have at least 1 double bond. If it was nonine, it would have 1 triple bond. And then we just fill in the rest of it with hydrogens. So this first one is a problem that could show up on an exam. Or I could give you the structural formula and ask you what the name is. So I want you to know the prefixes, meth, eth, prop, but, and then the others are the same, and the suffixes ein, een, and ein. The second question I think is good to look at, but I won't ask you a question like that on an exam. To which family does this compound belong? We're looking at the part that's not just carbon-hydrogen. And so it's this part right here. It's a ketone. So this could be abbreviated R, and here's carbon with its double bond to the oxygen, and then we would abbreviate this perhaps as R prime to tell us it's different than this one over here. And then we go back and look at the table. So the ketone has this carbon-oxygen double bond and an R group on each side of the carbon. The aldehyde is very similar. but you have a hydrogen on one side and an R group on the other. The way I remember that is aldehyde has an H in it. The aldehyde has an H on the carbon. Ketone doesn't have an H, and so there's no H on the carbon. And I don't think it's worth spending a lot of time learning to identify those, but I just want you to know that they exist and to have seen them. Any questions? Yes?
Can we go back to this slide?
This one?
Yeah, where did the R come from?
Where did the R come from? Well, I'm trying to convert this into the same format as on the table, because it's hard, especially at this level, to know what you're looking at. So this is an alkane group. It's just carbon and hydrogen. So on that table, they abbreviate this as R, because this could be 3 carbons or 5 carbons. There's a whole bunch of different variations of ketones. And so when we reduce these to just abbreviations, it's easier to see what we're looking at. But this belongs to the ketone family.
And the second R, would that include the CH2 and CH3?
Yes. So this R prime includes both of those.
So when you say prime, that means more than one?
Prime is just used to indicate different than R. R prime, R double prime, R triple prime. That superscript prime is just to say it's like this one, but not necessarily exactly the same.
Because it doesn't have a triple hydrogen, is that why it's not?
So this one has 1 carbon, and this one has 2 carbons. So
Looking at the carbon thing.
they're similar, but they're not the same.
Because they're both hydrocarbons.
They're both
but they're not the
hydrocarbons.
Same hydrocarbon.
Right. One comes from ethane, and one comes from methane. And they would be named, this would be a methyl group, and this is an ethyl group. They're similar, but they're not the same, and that's all that the prime means. Do you have a question?
Yeah, for the first picture,
Mhm.
even though it's single bonded, that's just the little dashes, right? So why are there 4 for each carbon?
So the question is, on this structure, why are there 4 lines for each carbon, right? Because carbon always forms 4 bonds. Always. Qualify that slightly, but in this class, always. Okay? And so the name nonane, the ane tells us all single bonds. The prefix non tells us 9 carbons. They don't need to tell us how many hydrogens, because we can figure it out.
What would nonene look like?
What would nonene look like? Okay, so there are actually a whole bunch of different ones, but we don't need to worry about that. So for nonene, we would have to put a double bond in here somewhere. Let's just be simple and put it on the end here. So we need to put I didn't mean to do that. We need to put a double bond here. But we can't just throw the double bond in, because now those carbons have 5 bonds. And so what we have to do is remove a hydrogen from here. So now the carbon on the end only has 4 bonds, and then we have to remove one from here as well. And so that would be nonene. If I asked you to draw the structural formula for nonene, I would accept the double bond anywhere that you drew it. I'd say that's good enough.
What would the name of the bottom one be?
What would the name of this one be? Well, there's a couple different ways to name them. One would be ethyl methyl ketone. That's the common name, ethyl methyl ketone.
You didn't say dye for the 2.
No, this is ethyl, and the ethyl tells me 2 carbons. So there's an ethyl group, and there's a methyl group on a ketone. Yes?
On the top one, if there's another double bond, it's still nonene.
If there's another double bond, would it still be nonene? It would be a nonene.
So that's NPK?
Pardon me?
The solvent, that's what that is? The
Ethyl methyl ketone.
Methyl ketone?
Yeah.
They sell that or
Yeah, they do.
like a thinner for me.
Right. Yeah, some of these are excellent solvents, and you can buy them at the hardware store. So what if this had two double bonds? Yes, it would be a nonene. There's actually multiple nonenes, depending on where the double bond is. And in organic nomenclature, we have a method for indicating where the bond is and how many bonds there are. But we're not going to worry about it. Any other questions? Okay, end of chapter 3.